You.
So the next speaker is Pierre Ramond, who is going to speak momentarily on higher spin massless particles.
Mm-hmm. Thank you. Pointers. Oh, excuse me. Okay, there it is. Now, I'm going to start with a preaching page about things. As you know, I haven't been doing string theory for a long time. And, and when I was doing it, I hardly knew it was string theory. But coming back into the field there, I've been attracted by the mysteries of M theory more than anything else. And therefore, looking at it from a point of view of kind of group theories and things like this, I kind of got interested in what the peculiarities of SO9 as the little group of the 11-dimensional theory. Now, as you all know, SO8, the little group in 10 dimension, has magical properties and SO9 does not. So the question is, now that we know there is a particular very interesting and mysterious theory in 11 dimension, what's so special about SO9? That's kind of the thrust. This has led me to look at various things which have been all weird and in fact kind of, how should I say, Don Quixotic. I mean, kind of chasing after windmills and with Sancho Panza, Lars Brink. Now, don't tell him I said that, please. Okay. So, from my point of view, anything which involves n equals 1 supergravity is worth a look, and SO9 is not as pretty, and etc. The second thing is that we don't know anything about SUSY breaking, except we have 1,001 ways to parameterize it, but we really do not have any favored way of doing it. I remind you of an analogy which I like, which is in the old days, before most of you were born, there was such a thing as chiral symmetry and recognized in pion-nucleon pion-nucleon physics, which was then recognized by some people to be spontaneously and explicitly broken. But in terms of pion and nucleon variables, it was rather mysterious why it happened. And of course, the resolution of this was the quark picture NQCD, which gave a very natural explanation of how it happened. But in other words, you had to go to new variables in order to find a natural way of expressing the breaking. And I kind of think that perhaps the same thing will occur in string theory, namely that the theory in these variables do not seem to show any propensity to break, but maybe in terms of new variables, it might lead to a new mechanism. And therefore, my interest is that to try to find all realization of supersymmetries, no matter how crazy they look. Now, I was led to, in this quest, to considering massless particles which spin greater than 2. And just to remind you that I do know a little bit what I'm talking about, I know this is strictly verboten. There are lots of lore on why you should not use massless particles that spin greater than 2. It starts with Randy Duran, Case, Gaziorovich, Witten, and Weinberg. And then in the old days, when supersymmetry was found, was discovered in space-time, in 4-dimensional space-time, there was a question whether spin 5/2 could be coupled to gravity, and there were various works by Mark Grisaro and Peter Casanova and DeWitt and Friedman, Deser, Aragone, and stuff like that, and all these people came to the conclusion it was not possible. The point was the following, that if you have a higher spin massless particle, actually a higher spin particle, you've got lots of indices, and you've got lots of zeros in them, and you've got lots of ghosties, and you have got to get rid of them. So you have to basically have a lot of gauge invariance. In the process, then you couple gravity to it, and you find the two don't like each other very much. And in fact, the commutator of the two gives you something proportional to a Ricci thing, and then the next reflex is, can you get this from a Lagrange, from an extra terminal Lagrangian? And the answer is no, in flat space-time. It turns out if you go to curved space-time, you can do it. Misha Vassiliev, who is in the audience, spent a lot of time looking at this in non-flat space-time. Or if you want, another way to do it is you run out of derivatives. But the thing is that many of these theorems don't apply if there are an infinite number of particles, but then there is no proof that basically it can be done because there is no pudding. Now, so where do these things occur? Well, I would like to remind you of two places. One is in, the previous speaker mentioned Mr. Wigner in terms of random matrix models. Well, this is Mr. Wigner, of course, wrote also the representations of the Poincaré group. By the way, I understand he had been exiled from Princeton, and he went to Wisconsin to do it, and then he was called back after he did it. He found those continuous spin representations, which I will talk to you about. Those are massless representations, which contain an infinite number of velocities. It turns out that they are rather, and Wigner tried to find some use for them and failed, and many other people have as well. Maybe that's a message, but I have tenure. Now, the second part is Euler triplets in 11 dimensions, which I will be talking about, and some of you have already heard me talk about. So let me remind you a little bit what those infinite spin representations are. I will generalize them to supersymmetry. I will generalize them to higher dimension. So let us start with the light cone Poincaré algebra, what's known as the Bakry-Cheng representation in some quarters. So you have the Hamiltonian P minus, you have the variables, etc. And you've got all kinds of kinematic guys. And then you have the dynamic animals. These are the more complicated ones. And in the representation for the boost, which are the dynamic boost in Dirac's word, since we're celebrating today Dirac, it's good to be on a light cone. What happens is that in terms of the little group, Sij, you have basically the following relationships. You have basically a vector, T sub I, in there, which commuting with itself gives you m squared times Sij. Now, if m squared is different from 0, that's fine. But if m squared is 0, you have two possible ways of looking at it. Now, in string theory, for those of you who remember the original way of doing string theory, basically, that's the commutator that doesn't work unless you are in 10 or 26 or whatever dimensions because of normal ordering. So what happens now is that if m squared is different from 0, okay, then it's very simple because you divide by m and you complete the higher representation. Oh, it's windy here. Okay. And that's fine. If m squared is 0, then the two t's commute and you have two choices, one of which is that they're 0, and this leads to all the normal representations that you're familiar with, the photon, the neutrino, the what have you. If Ti is different from 0, though, this gives rise to to these strange massless representations. And what happens is that they're characterized by a space-like vector on a transverse plane, which value is non-zero. Those are the continuous spin representation. One way to see how it goes is that the Casimir operator of the Poincaré group are, of course, p squared and the square of the Pauli-Rubansky operator. And that's, in this case, p squared is 0, but w squared is not 0. It's equal to the length of this vector. And another way to see it is that when you take a state characterized in this representation, you can expand it, of course, in the basis of helicity states if you want, but you've got an infinite number of them. Or another way, if you apply a boost in a frame where pi is 0, the value of the boost increases the helicity by 1 unit. So the minute you boost your state, you generate with a finite boost all the other guys. And Wigner liked those representations, and many times he tried to make use of them, but he failed, and so has everyone else. And these would be the only unused representations, because we know about tachyons, which are used, if nothing else, as signs of trouble, but nevertheless they're used. And the others, of course, we know. So if you boost by a finite amount, you change helicity by 1 unit, and you've got two representations like this, which Wigner called Xi, whatever it is, some Greek name, Xi and Xi prime. And those, of course, are related by supersymmetry. You can go from integer to half-odd integer helicities. Now, in higher dimensions, how does this go? Well, in higher dimension, you fix the direction of, you still have exactly the same thing. You have a direction, you have a vector like this. And so it's rather interesting because these representations then get labeled not so much by, since you have a fixed vector in this space, they get labeled by the transverse vector. So for example, in 11 dimensions, these representations would be labeled by SO8, the happy group. the good group. Now, in dimensional, that also gives question about dimensional reduction, because in a sense you could start with one of these representations, and as long as you limit yourself to the transverse plane, you don't have any problem. The problem, though, is how to get from Ti finite to Ti equal to 0. So the question is, does Ti play a role? So this is something else. But these representations are basically labeled by the little group of SOD minus 3. But they do exist, and they're happy. And you can have supersymmetry on them. Okay? So the meaning of T sub I have no idea. The question, is it related in some way to some dynamical object? I don't know. And as I said, the transformation in the plane orthogonal to T sub I are totally normal. So you go one less dimension. Now, supersymmetry turns out to be rather easy to implement in all of these. And you have basically another representation of supersymmetry, which people, to my knowledge, really, they may have looked at it, I don't know, but I haven't seen anything on it. And those are infinite dimensional representations on which you have bona fide supersymmetry working. For example, in 10 plus 1 dimension, you have, for instance, you basically have, if you wish, at some level, the spectrum of type 2A, and then an infinite number of friends with basically shifted by a vector helicity, something like a vector quantum number. And you have an infinite number of them. And of course, this is not very good from the point of view of any field theory, because there are all these no-nos. But the question is that such representation exists. And the interesting thing now, since we know that we have to look at higher groups, the question is, where do those representations lie in higher groups, in a conformal group, de Sitter group, etc., when you reproduce it, when you decompose it in terms of the Poincaré group. So the question here is simply a question of, how should I say, labeling this representation, but I wanted to draw your attention to their existence. They exist, they are there. There's probably no local field theory associated with them. I should tell you that there is a literature on this. This is something else. If you want, see, one thing we try to do is that if the vector T sub I exists, then if you make a finite boost, you get all the helicities because you get Ti squared, da 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 da. But the question, if Ti were nilpotent, then it would stop and you get a finite number of boosts. So we tried to do it and implement with supersymmetry. Then you got massless things with central charges, which meant that you had ghosts. So again, that was a sick. We're in a hospital ward right now. We're just basically playing with sick things. Now, well, as long as you can cure a few, it's okay. Now, so Wegener thought the CSR would be useless. He said things about infinite heat capacity of the vacuum and things like this. And he tried over and over to use them. A bunch of people back in 1970s, Larry Abbott, Hirata, tried to quantize these theories in an interacting thing. They either found troubles with causality or with locality. And so this was dropped. Mr. David Zoller wrote a Lagrangian for it in order to reproduce the Bargmann-Wigner equation associated with those representations. And he found that the Lagrangian was proportional to the acceleration of a particle, and namely a high derivative theory, using this Russian formalism where you just go several steps down. And so the question is that but these are curiosities and one should pay attention to them. Now, so let me now turn to the second topic where massless infinite dimensional, with massless representations come up. So let's go back to this question of supersymmetry and SO9. By the way, I should tell you that with this representation, you do link SO8 with representation of the Poincaré group in 11 dimensions. Now, what that has to do with the price of cheese, I don't know, but at least you do have SO8. Now, supersymmetry and SO9, SO8, as you know, is the Mercedes of the groups, and SO9 is probably like the Trabant. It's not very pretty. But E8, of course, which I will not talk about, is the Delahaye, and this is for your culture. In this, if you don't know what a Delahaye is, you should. Well, it's the French Rolls-Royce, but they didn't make it. It's very pretty. Now, okay. Now what we're going to find is that if you in this particular generalization of some patterns associated with n equals 1 supergravity, we find an infinite number of massless states which come in 3 representations of SO9, and they do not have supersymmetry between them, but in their spectrum, the notion of spin statistics is preserved if the number of fermions is equal to the number of bosons. And so the question is, does that lead to an infinite dimensional representations of supergravity? And this is extremely specific to SO9, so therefore it's specific to 11 dimensions. So let me remind you a little bit about this very quickly, because I'm actually completely running out of time. Okay. But then what is time? We've learned now. Anyway, so, okay. N equals 1 SUSY in 10 dimensions. Well, you've got a chiral superfield way of writing it in terms of variables, etc. And you've got these 3 animals here, which, well, these animals, and they're basically labeled the 3 representations of SO9, which describe N equals 1 supergravity. If you write it in terms of highest weight states, you've got 1, which is the highest weight of the 44, 1 the 128, and 1 the 84. I just learned this one actually is a product of something, and I'm kind of surprised by it, but it's okay. Now, these SO9 generators, you can write them out, etc., and I won't bore you with that. But what you find in them, by the way, is that there a bunch of structure functions appear, which actually are the same structure functions of F4. More on this later. Now, what is peculiar about these SO9s is the following, is that, of course, the number of fermions is equal to the number of bosons, so the dimensions of the 128 is this. But of course, this ability continues for the 3 of the 4 invariants of SO9 being a rank 4 group. So this is the guy that occurs in the beta function, you know. And these are high order invariants. And it fails at the level of the 8th one. And that is, by many people, notably Tom Cartwright in the old days, related to the fact that the N equals 1 supergravity is not a renormalizable theory. There's leakage. Because there's not perfect cancellation. And so, now the question is, which I looked at some time ago, are these kinships between different representations shared by any other representations of SO9? And it turns out, amazingly, that the answer is yes. And it comes after talking with some mathematicians and then rediscovering later that people in the context of Kazama-Suzuki coset construction that come across such things, is that if you embed, there are 3 equivalent ways of embedding SO9 into F4. That's like I spin, U spin, and V spin, exactly the same thing. And that leads to a character formula, which is complicated. And it relates, basically, it tells you that some guys minus some other guys is equal to 3 guys. There's a million, there could be 5 million of them, and here there are 4,900,000 is equal to 3. This is a big magic. And this leads to 3 representations of SO9. And one thing interesting is that for SO9, the last Dinkin label is odd, means it's a fermion. So if A3 and A4 are even, then the number of, this is the largest representation. So the number of fermion is equal to the number of boson. We'll come back to that later. Okay. It turns out that this actually, this index, this formula can be viewed and was interpreted by Costant as an index formula for an operator, which actually is the beginning of the conformal generator. Somebody's operator, I forgot his name, and basically starts something like this. And if you solve this equation, you find an infinite number of solutions labeled in terms of SO9. Okay. So, and these solutions, the trivial one is the supergravity. All the others are something else. So let me now very quickly tell you about it, the best way to do F4. The best way to do F4 is by one of what's known as the anomalous Dinkin embedding of F4 living in SO26. So you write F4 in terms of 26 variables, because that's the fundamental representation. So you got 16 animals that are Bose commutators, even though they're fermions. So right away you say, what if I'm going to think of this as a space group, then a fermion should have anti-commutators. So that's a priori you would say, I will not go any further. You've got 9 guys which are vectors, and you've got 1 guy which is a scalar. And you write down, remarkably simply, the generators of SO9 in this way. This construction is due to Tom Fulton from a long time ago, which generalized Schwinger's construction for SU2. Okay. Now what you do, and let me tell you one more thing here, is that what you do is that you rewrite these oscillators here in terms of coordinates, u0, ui, and zeta. Why, I don't know, but that's what I did, because somehow it would look more geometrical, since I notice all you guys do is write metrics. So in terms of this, it's better. So you find actually that the solutions of this equation can be written very much the same way as the supergravity solution. So you have three fields corresponding to three representations of SO9, and they have these internal objects as coordinates. Okay? And to each solution corresponds one representation of F4, and which, if A3 and A4 are even, then it works out that you have the number of bosons is equal to the number of fermions. So let's take an example. For example, the one that corresponds to A4 different from 0. The particular dependence of these functions is of that form. These are spinor variables. Okay? So you see that if A4 is odd, you've got an odd number of objects which are Bose, which have yet fermionic thing. That's the no-no. However, if A4 is even, then you do recover spin statistics. And in this language, you recover the number of fermions is equal to the number of bosons. I don't understand this at all, but that's it. That is a fact. So in this solution space, the number of bosons being equal to the number of fermions, which is not necessarily supersymmetry, but maybe a beginning, is connected with the fact that you don't mess up with spin statistics. Now, it gets to be more complicated. The behavior, the functional dependence of these extra functions for different values of the Dynkin indices come out to be like, this is like an area, for example, in these new coordinates, etc., etc. So, and again, the business about spin statistics tells you that if you have, you see here you have automatically, you see here you have linear functions of the zeta, so A3 must be even, and that's again number of fermions is equal to number of bosons. So in this solution space, the number of fermions being related to the number of bosons is actually they are one and the same. So the question, what does it mean? Well, of course, I don't know, because I would not have presented it this way if I'd known. Okay, so the lessons of this, for example, is that when the dependence of these functions is quadratic on zeta, that means no connection, no problem with spin statistics, number of bosons, number of fermions are the same. And in this case, for example, the internal variables either look like volumes or surface areas. They set themselves up in this way. Okay? In particular, for example, a particular series is generated from one to the other by two forms. Now, if you were to couple a two form to n equals 1 supergravity, or the superparticle in 11 dimension, you lose right away supersymmetry. But the question is that does this infinite array of things actually give rise to something more? And then the question that's interesting is that if I limit myself at least to number of bosons equal to number of fermions, that's a step in the right direction. But what I need to prove and to show is that actually there's more symmetry by considering all of them. And I will so give speculations, and I have actually some thoughts on how to go about it. Let me take the example of a gauge theory. In a gauge theory, you have a finite multiplet. And in a finite multiplet, you transit from one to the other by emitting gauge bosons, external fields. And let me assume that perhaps each member of this is like one of these triples of representations. And I go from one to the other by emitting a bunch of fields like this. So I'm hoping that actually these form an infinite dimensional representation of something. I don't quite know what. But I'll try. So the question is, at the moment, the work in progress is try to couple this, build the current with a two form, because two form looks good. I mean, two forms. I love two forms, and they're basically, you know, they make you dream about surfaces, geometry, and they make you sound, you know, like you know what you're doing, and this is very good. So perhaps there is something there. The other thing that is interesting is that excuse me. The other thing that's interesting is, This is an eraser. That's not going to work. Although, that may be okay, too. Okay, well. No, there's there? Oh, there. Oh, thank you. That's okay. I can write it here. The thing is that if I look at the delta of the I8, that means the thing that makes it not renormalizable for n equals 1 supergravity. That stuff is proportional to the dimension of an F4 representation to which that triplet comes from times a number. And so the question is there any way in which when I sum over an infinite number of them, this actually could vanish in some way, or at least have a finite value, which then I could cancel with something else? At that point, I would stop the leakage. And so perhaps that is something that one should be looking at, because in the language of the local field theory, the leakage of the I8 is the beginning of the troubles, beginning and the end. Okay? So, repeating myself a little bit, the currents, so ET means Euler triplets. By the way, Euler triplets because there's something beautiful there, absolutely beautiful. And like many beautiful things, it should be hung in a wall and never used, but it's beautiful nevertheless. There's this coset space, F4 over SO9. F4 over SO9 is a very, very special coset for mathematicians. It is a coset where there's a projective space, of course, that's fine, but it's not any projective space. It's the Mufang plane. It's a very special projective space. I said the word Mufang and it comes up. Now, so, okay, sexist. Now, and so what happens is that it is very unique. There's also another aspect, another thing in physics where the same coset comes up. It's something called the exceptional Jordan algebra, where Pascual Jordan and Wigner and von Neumann tried to write algebra of observables for quantum mechanics and found, of course, it's mostly n by n Hermitian matrix models. But there's also a 3 by 3 Hermitian matrix over non-associative numbers called octonions, and that this has been always a source of very interesting stuff, very, very weird things. The question is, of course, that its variables are a 16, a 9, and a 1. So everything looks kind of suggestive, but of course no one has made the connection. So the question we're trying to do right now, very simply, is to try to couple this system. So you have basically the superparticle in 11 dimension, and you have the other Euler triplets like that. And the question, can you make a transition between one and the other? And you will lose supersymmetry for sure, but the question, will you recover some sort of symmetry when you look at the whole thing? So this is the kind of stuff we've been playing with. It's Sancho and I have had a lot of fun, and it also has the advantage that basically no one else is working on it, so it's good. And I kind of always like that, because in my little swamps where I live, the communications are not very good, and we only go back to the company store once a week and find out the news. So, but nevertheless, it's a very exciting thing, and the reason why I think this is important to look at, unlikely as it may be to give you anything, is that you are really bound to look at any mathematical funny structure having to do with 11 dimensions, because there's this big animal that lives there, and it's lurking deep in its cave, and it's only known through its reflection on the walls. It's very the dialogues, on Plato's cave, you have the analogy where you have the reality is only seen through the reflection on the walls. Yeah. Well, that's a little bit like M theory right now, because it's only seen really in detail through its compactifications. And so it's very nice to go into the layer of the beast. And so you're bound to investigate any peculiarity with 11 dimension. And I claim there is one having to do with this very weird coset. And the question, of course, that would lead you to exceptional groups playing some role in space-time description, which would be very nice. We already know they play a great deal of role in charge space. The question, can they play equivalent role in space-time? Thank you.
Do we have any questions?
Probably not.
Comments after the talk? Ed?
In the first half of your talk, where you commented very briefly about Vasilyev's work on high-spin massless particles, is it conceivable that this continuous spin representation, if you deform to negative cosmological constant, would give something that would either be equivalent or possibly a slight improvement on the Vasilyev stuff?
Yeah, in fact, we're supposed to talk at lunch today. Yes, they're very good, absolutely. Absolutely. And the question is, what are, as I said, you go into higher dimensions, higher group structures, and you see how these animals live in there and what it is, and then you try to give a geometrical. Yeah. The one thing that's interesting about them is that at least, they are not, by themselves, they certainly don't look good. But maybe they look good in a different context. Okay. Yeah.
Yeah, Nathan Berkowitz from IFT. The lowest, if you look at massive representations of the open superstring, just 10-dimensional open superstring, the lowest massive representation is the same as 11-dimensional supergravity. It's just S09. Could the higher massive representations of open superstring be related to yours?
No. It looks like there are far fewer states, in fact. No.
Misha Vasilyev, Lebedev Physical Institute. I have a little comment on this relationship with these continuous spin representations and harassment systems. It looks very much like these continuous spin representations can be understood as a rather non-trivial and non-local deformation of the higher spin systems, which makes sense only in the flat space limit. In ADS, the symmetries is decreased, so one can consider Dutch systems, but symmetries are less there. Okay.
How can the diffraction on the wall be reality without the brain?
Oh, you're talking, this is a Platonic question. Should I give you a Platonic answer? I don't know. I'm only a physicist. Yeah. Okay, yes.